Get started. So I'll chair this session. So we welcome you all back. Some in the morning, some in the afternoon, some in the very late evening, like Michael. And Michael will be giving the second of his 3 lectures. And I'll just remind you, if you have questions, you should just feel free to unmute yourself and ask them. Or if they're less pressing questions, you can go to the chat and address the question to everyone. If you address it just to Michael, then he might not see it. And even if he sees it and addresses it, other people might not know what he's addressing. So better to just address everything to everyone and go from there. Okay, well, Michael, why don't you take it away?
All right, thanks, Ivan. Yeah, so I've actually opened the chat window next to the lecture window. So if somebody types something in there, I'll probably see it at some point. But yeah, I'm not sure how responsive I'll be to that actually during the talk. Okay, so so for this lecture, it's possibly going to be quite a long one compared with the previous one. So there's a possibility that some of the material will spill over into tomorrow's lecture. But anyhow, I guess we'll see how we go. So I'm going to be talking about these 2 families of symmetric functions. Let me highlight it. So I'll be talking about whole-Littlewood polynomials and the q-Whittaker polynomials. And both of these are really sort of celebrated and famous classical families of symmetric polynomials in an alphabet of n variables. And so I'll say a little bit at the beginning of the talk about some of the sort of historical aspects of where these symmetric functions actually come from. And I hope that people who are accessing the chat can possibly put good references in there if you happen to know of any. Of course, in all instances, the first reference for any of this kind of stuff should be McDonald's book on symmetric functions and whole polynomials. So indeed, most of what I'm going to say, you can just find it in McDonald's book. So we're going to be talking about those 2 families of symmetric functions. And I've just drawn this little picture here, which is just a very sort of small miniature of the basic symmetric function landscape that is probably familiar to many people. And so at the top of this hierarchy, well, arguably at the top, some people would say that there are other things beyond this, but certainly in terms of what you'll find in McDonald's book, this is really the top of the hierarchy, the McDonald polynomials. I won't be talking about those today, but just as a comment that the McDonald polynomials, they depend on an alphabet of n variables in which they are symmetric, and they also have 2 additional parameters, usually denoted by q and t. Here we're not going to see the appearance of the t parameter. I'm going to be using the q parameter for everything, including for the whole-Littlewood polynomials, which is somewhat non-standard, but I've done this because we introduced q in the previous lecture, and I just want to be notationally consistent. All right, so McDonald polynomials, they degenerate both to the whole-Littlewood and the q-Whittaker polynomials. And we're also going to talk about a certain technique, which is quite an old technique in exactly solvable quantum integrable models, which is the idea of fusion that goes back to the Leningrad School in 1980s. And so the observation is that by taking a whole-Littlewood polynomial and performing fusion on it, you actually get to the q-Whittaker polynomials on this side here. And so sort of this step here, you won't really find this step, to my knowledge, in McDonald's book, for example. So he never really talks about this particular procedure. And if you want to go even further down the hierarchy, you can specialize both of these, the whole-Littlewood's and the q-Whittakers, and you'll get down to the short polynomials, which sort of live at the base of this hierarchy. And of course, all of these families of polynomials, they serve a very important role in integrable probability, notably, notably via the short process in the case of the short polynomials, and also via the McDonald processes in the case of McDonald polynomials. So certainly, learning about these families of symmetric functions very useful if you want to be doing probability. Okay. All right. So now let's say a little bit more about what we're actually going to be doing. So in this particular landscape, some of those families of symmetric functions, they admit certain types of explicit formulas, which I've referred to here as beta ansatz type formulas. And so this is a similar sort of symmetrization formula as we saw in the previous lecture when we were looking at the 6 vertex wave functions. And so when you talk about these kind of symmetrization formulas, both the whole Littlewood polynomials and the short polynomials, you can express both of these explicitly as sums over the symmetric group. And indeed, in the case of the short polynomials, probably as everyone here knows, short polynomials can be written as determinants. And if you take the determinant and just perform its Laplace expansion, you get a sum over the symmetric group. And that is exactly the type of symmetrization formula that we have seen already. So both of these have a symmetrization formula. But if you go on to the other side of the picture, I would argue that the q-Whittaker polynomials, these are something that's more combinatorial in nature, in the sense that if you actually take those things as they depend on this alphabet of x variables, and if you expand that over the monomial basis, what you find is that expansion actually has coefficients that live in this set here. So they're going to be polynomials in Q with positive coefficients when you actually work out those coefficients. And likewise, in the case of the Schur functions, it's very well known that when you expand over monomial basis, the coefficients will just be the naturals. Okay, so yeah, it's for this reason that I say that q-Whittakers are sort of combinatorial in nature, because they have this positive expansion when you expand over the monomial basis. And so really you see the Schur functions are very special. Somehow they live at the base of the hierarchy, and they have not only the symmetrization type formula, but they also have combinatorial formula in terms of Young tableau, as I'm sure is well known to many people here. Okay. So let's talk a little bit more about polynomials. So whole Littlewood polynomials, they really have, well, origins that sort of look quite unlike anything to do with symmetric functions. They actually arose as polynomial representations of the generators of a certain algebra, which is known as whole algebra. And so whole algebra is an algebra in which you have generators indexed by partitions, and these, when you multiply two of these generators and expand over the generators, you have some structure constants, which are known as the whole polynomials. And they have certain interpretation in terms of finite p groups, which I'm not going to say anything about. But nevertheless, this is really where the whole algebra comes from in terms of these whole polynomials. And so you then look at the generators of the whole algebra, and you ask yourself, can I represent them in terms of objects that live in the ring of symmetric functions? And when you do this, you get precisely the whole Littlewood polynomial. So this is I guess the origin of where they come from. But we're going to be looking at them in sort of very explicit way. So for us, these are going to be one parameter deformations of the Schur polynomials and also the monomial symmetric functions. So in the case q is equal to 0, you get the Schur polynomials, and for q is equal to 1, we get monomials. Okay, and as advertised at the start of the talk, they have a symmetrization formula. So this is the formula. And we'll take this as our definition of the whole Littowitz. So they're indexed by a partition, lambda, and conventionally, we're going to take the partition here to have a definite length. So it's going to be of length n, which is fixed once and for all. And we're going to allow ourselves to have parts of size 0. So basically, the tail end of this partition, as many of those parts as you want, can actually be equal to 0. So this is going to be our partition. And then the formula is as follows. So whole Littowitz polynomial is going to be represented in this way. So you have some overall normalization, which we don't need to say too much about. Now, the important part of the formula is given here. And notice that it's very similar to the type of formula that we saw yesterday for the 6 vertex wave functions. So again, I have a sum over a symmetric group. I have this permutation, which is acting on the x variables. And if I look here, I actually see I have precisely the same scattering factor that I have in the case of 6 vertex model. And then I have this kind of product of one particle configurations here, product from I equals 1 up to n of xi, where the exponents are just the parts of the partition. So this is going to be the definition of the whole Littowitz polynomials. And here in the normalization, I'm using this notation, which is more or less standard. This mi of lambda is just counting the part multiplicities of the partition. So in particular, it's the number of k's such that lambda k is equal to I. Take the cardinality of that set, and that is going to be the part multiplicities of the partition. All right, so let's hold it to it. I should mention as well, I didn't say it earlier, the notations that I'm using here are completely non-standard. It's certainly not usual to denote whole Littowitz by h's, and it's certainly not standard to denote Macdonald polynomials by m's. Usually in the literature, all of these are just given the letter p, which I find to be quite confusing if everything is just called p. So that's the reason why I've done it. But certainly if you look in Macdonald's book, he's not using this notation. So this is just a word of caution. Okay, so we have a question from Rick. Can this formula be interpreted as a sum of non-intersecting lattice paths? So we will see a lattice path interpretation of the formula, but certainly this is not non-intersecting lattice paths. Yeah, it's a little more complicated than that, but it does have a nice combinatorial interpretation. Yes. Okay. All right, so then we come to a theorem, which we're not going to say anything about the proof. And that is that the whole Littowitz polynomials satisfy a remarkable summation identity, which is usually referred to as Cauchy identity. And so what it is I take a product of two whole Littowitz polynomials with two different alphabets. So here I'm using x for the first alphabet, and for the second alphabet, I've chosen to use z's because y's are sort of already in use and I don't want to touch them. So this is what we do. We take a product of two whole Littowitz and we multiply by some, again, overall factor, which is not too important, and we sum over all partitions, lambda. And so the claim is when you perform this summation, at least if you interpret this thing as a formal power series, you can actually sum it up and you get the answer here on the right-hand side, which is just this very simple product in terms of the x's and the z's, and also the q parameter. So it's a very beautiful formula, and closely related with the fact that these polynomials are actually orthogonal with respect to a certain inner product. So the sort of the orthogonality of the polynomials and the Cauchy identity really go hand in hand. So certainly if anyone is interested in this, then the best place to look is in chapter 3 of McDonald's book. Okay. And also, I guess, probabilistically, these Cauchy identities very important in, well, not just in the case of whole Littlewood polynomials, but if you go all the way up to McDonald polynomials, the Cauchy identity is really the foundation for the so-called McDonald measure, which is a probability measure that you put on partitions. And this is really the foundation in turn of the McDonald processes. So these Cauchy identities, there's a lot of mileage behind them. You can really do quite a lot with them. And they also have, you can actually prove them as well using integrable vertex models. So there is actually integrable vertex model proofs of these types of identities, which have emerged sort of in the last 10 years, some of which I have been involved in. So certainly, I hope if anyone is interested in this, then you can ask, maybe we get some references put in the chat if anyone knows them offhand. Okay, so these are the Holidowitz. All right, so now let's say something about the other characters in the story and really the title of the lectures. So I guess I should finally say something about q-Whittaker polynomials. So these things, they have origins, unlike the whole Littlewood polynomials, which have origins of really representation theoretic origin. The Whittaker functions, they're really mathematical physics type objects, and they really arose as joint eigenfunctions of a certain integrable system known as the total lattice. So the total lattice, it has a Hamiltonian which can be expressed in terms of certain differential operators, and the joint eigenfunctions of the Hamiltonian are in fact Whittaker functions. And they have a Q-deformed version, which you can think of some sort of quantization. And these are precisely the q-Whittaker polynomials. And there is a degeneration of these where you send q to 1 in quite a non-trivial way, and they will then degenerate to the classical Whittaker functions under this scaling. So yeah, we're going to be looking at the q-Whittaker polynomials. And so we're not going to give the definition in terms of eigenfunctions of total lattice. We're just going to define them straight from the McDonald polynomial theory. And so the definition we're actually going to give, it's a little bit of a cheat to actually give this as the definition, but I find it's expedient for the purposes of the talk. So the definition is going to be that the whole Littlewood and the q-Whittaker polynomials, you can actually pair them together and you get what is known as a dual Cauchy identity. So this one looks a little bit different to the previous one. So I still have a whole Littlewood polynomial here in the alphabet of the z's, and I multiply this by now this w. So this is going to be my q-Whittaker polynomial. And here the partition that indexes this polynomial is actually the conjugate partition of the lambda that we start with. So hopefully everyone knows what is conjugate partition, but just in case you don't. So if your lambda is some sort of Young diagram that looks like this, the conjugate partition is what you will get. Instead of reading the rows, you would read the columns of the Young diagram, and that will give you lambda prime. Okay, and so in this case, when you perform the summation over the partitions, you again get a product, but it's rather different this time. You get this product, and it's actually independent of Q. So even though both of those polynomials depend on that quantum parameter, you actually find that it doesn't show up on the right-hand side at all. And so we're going to use this as the definition of the q-Whittaker polynomials. Why does it serve as a definition? Well, the reason is, of course, I can take that product on the right-hand side and I can decompose it in terms of whole letter-word polynomials in the Z alphabet. So I didn't say it already, but whole letter-word polynomials, they comprise a basis of the ring of symmetric functions in n variables, and so I can actually decompose that product in terms of whole letter-words, and when I do that, I will get some coefficients, and the coefficients will have to be the q-Whittaker polynomials. So this is the definition that I'm going to use. All right, so I'll just have a quick look at chat here. Okay, there's a question there about fusion. Okay, I probably shouldn't spend too much time reading. Yeah, so I hope people can help out in the chat. All right. Okay, so this is the sort of the primer on the functions we're going to be looking at. And so now I would like to say something about how you can actually get to them coming from the 6-vertex model, which is really the sort of one of the aims of these talks, to show how you can do this. All right. So the idea is going to be, we have those 6-vertex wave functions that depend on the 2 alphabets. So you have the X alphabet, which are the horizontal variables. You have the Y alphabet, which are the vertical variables. And what we're going to do now is start to specialize those variables in certain ways. And the way that we do the specializations is a little bit intricate. So let's have a look at what happens. So sort of as an illustrative example, we're going to go back to the one particle wave function that we saw in the previous lecture. So I've just written it down again here. So it's just a product, just a rational function depending on the single variable x, and depending on the y variables from y1 up to yk we have here. So this was just the partition function that you get when you have one row. And what we're going to do now is we're going to take the y variables, y1 up to yk, and we're going to group them now into what I'm going to call bundles. Okay, so what do I mean by bundles? Well, let's just have a look at the picture that one gets. All right, so I'm literally going to take my lines now, and I'm going to split up those little k lines that I have. I'm going to split them up as shown here. So I'm going to have bundles now. This is going to be the 0th bundle, the 1st bundle, all the way up to the kth bundle. And the cardinalities of these, so this is going to have J0 lines, J1 lines up to JK lines. And so here, you know, we're assuming that little k, you can take it to be as big as you want now. So for the purposes of this computation, we can take little k to be really big so that we can have lots and lots of bundles, and the bundles themselves can be big. Okay, so that's how you should think of it. And the only condition we have here, of course, is that if I take the sum of all of those cardinalities, they should sum up to little k itself. Okay, so this is the idea of bundles when you apply to this one particle wave function. Okay, so now let's have a look at what happens to the formula itself when you actually do this bundling. So what I'm going to have now is I'm going to have my y alphabet and it's going to come with these superscripts now that tell me which bundle I'm living in, right? And so in that case, the product ends up looking like this. So, okay, it's a bit of a ugly expression, but literally all I've done here is just, take my, my y1 up to yk that I started with, and I've just relabeled them all in terms of these superscripted variables. And you end up getting this. Okay. So here I have the first product, which is going over the bundles themselves. And the second product is sort of internal to each bundle. Okay, that's the way you should think of it. And notice that the final bundle is a little bit unusual. This one is sort of separate from the rest. And the reason for that, of course, is we see that in the final bundle, something different happens. So actually the particle actually terminates in the final bundle. So that's the reason why the final bundle looks a little bit different. All right. So what we're going to do now is start to specialize these bundled variables. And the specialization, what we're aiming to do here is to get some sort of telescopic cancellation when we do this. All right. And so to make things telescope, there is a very natural choice, which is just this. So I'm going to take the y variables in every single bundle to just be this geometric progression. So the base here is going to be s, which is some indeterminate, which for the moment we'll just treat it as an arbitrary variable. And the q here is going to be the thing that I have the geometric progression in. So I just have powers of q now. And so I do this specialization for every single bundle. Well, when we do this, it's pretty easy to see that just, by the nature of what we have inside of these products, when you do this, you're going to get telescopic cancellations. And at the end of the day, one ends up getting this, which looks a lot simpler than what we had above. All right, so interesting thing about this is now we sort of get two parameters into the game, where previously we just had the y parameters. Now we actually get parameters of the form q to the j. So recall the j's are the cardinalities of those bundles. And we also have this parameter s now. So there's a little bit more freedom living in this object. And so actually, if we specialize it carefully, we can actually transform this thing even further so that it's no longer a rational function in x. It actually transforms into a polynomial in x. And so really what we're heading towards here is when we do these specializations, eventually we want to recognize the whole Littlewood polynomials as arising directly from the 6-vertex model wave functions. So that's where we're headed to. All right. Okay, so that's the expression that we get. And there's one more important step. And that is when we look at this thing now, we actually see that this thing has become a rational function in this variable itself. So actually q to the j, for each of those cardinalities, this thing has become like a variable in its own right. And actually you can analytically continue now and extend this thing to a complex variable now, arbitrary complex variable. And when we do this, we then have the freedom to actually replace the q to the ji by the same parameter as we had previously. So we actually replace it by s to the -2. Okay. So this is all some computation that you can do. And at the end of doing all of this, we get now this expression here. Okay, which is starting to look simpler and simpler. And already you can see it's getting very close to the kind of monomial that you would like to have in the whole Littlewood formula. So, and let's just remind ourselves what the whole Littlewood formula looks like. So it was this one back here. And so certainly in that formula, we don't want to touch the scattering factor. I mean, this is already in the form that we need from the 6-vertex expression. What we're trying to do is somehow massage the rest of that formula to this thing here, which is just the simple monomial in the x's. Okay. So now.
Here, Michael, I have a quick question. So in the star formula for the q to the ji equals s squared,
Yes.
I might be a little bit confused, but how is that formula consistent for all ji's? Aren't they different numbers?
Yeah, that's right. So when we start off, the j's are some integers, right? But then when you actually perform this principal specialization, you find that the object only depends on the j's via q to the ji, right? Which then becomes like a parameter now. So actually I have now k plus 1 of these parameters, q to the ji, and they're all independent actually. And so then I choose them to all be equal. That's the point. So then I choose them to all be equal to s to the minus 2.
So it's kind of a formal replacement.
It's a formal replacement. Yeah.
All right.
I mean, maybe I don't want to say formal, but really, you know, there is a sense where you start off with this thing here, where j is an integer, but then you can actually analytically continue so that j actually extends to all complex parameters now. So there's a way of making this precise via analytic continuation.
Okay, I see. Thank you.
Okay. All right. So this was a little computation in the one particle case. And if we do it in the case of n particles now, well, there's not really much which is substantially different. So in that case, we're going to have a picture of the form that's given here. So now I have my n particles, which coming in from the left as previously. And again, I bundle up my y variables. And so what I do now is, so previously when I was looking at that capital F function, I had the little k's, k1 up to kn, which were the coordinates of the outgoing particles. And so what we're going to say now is that ki is actually living inside of the bundle capital Ki. And within that bundle, we assume that the particle is situated as far to the right as possible. So you see here, this thing is sort of pushed all the way to the right edge. Here I actually have two particles that live in that particular bundle, and I also push them all the way to the edge of the bundle. Okay, so henceforth we restrict ourselves to the situation where we bundle the lattice up into these vertical segments, and within each of the bundles the particles are flush to the right. Okay. So that's what we have, and then if you repeat the computation that I did previously, so the specialization that I called star. So just to remind you, the star specialization happens in 2 steps. So the first step is to do these geometric progressions for the y variables, and the second step is to do this, this replacement of the q to the j's. So if I do this star specialization now to the 6-vertex model wave functions that have been bundled up in this way here, what you end up getting is this formula here. Okay, so I have some junk at the front, which I don't care too much about, but the important part of the formula is really what's written here. Okay, so again, we have the scattering factor that we want. And now we see that this thing is actually getting very close to the monomial that we actually desire to get whole-little with polynomials. And so actually, in the form that is written here, so this is a family of rational symmetric functions now that was actually introduced by Alexei, and then further developed in works by Ivan and also Leo Petrov, and other authors as well. Yeah, these things here, there's some rational symmetric functions in the x variables, and there is a limit of those which will actually give you now whole Littlewood polynomials. And so here is the first key result. So I take a partition lambda, and I'm going to abuse notation slightly now and use the same letter as I did before. So f sub lambda, this is going to be the 6-vertex wave function for n particles, which has been bundled up in the way that was shown in this picture here. So this is really f lambda, this quantity here. It's just that now I don't use the capital K's, I use a lambda instead. Okay, so this is f lambda, and we have the assumption here that particle I is leaving the lattice in the bundle lambda I. So what do I mean by particle I? Well, this first one here, this is particle number 1. And so this is leaving the lattice in this bundle here. So this bundle, whatever it is, this would be lambda 1. And then this is particle number 2, and this is leaving the lattice in this bundle here. So this, whatever this bundle is, this is going to be lambda 2. Okay. So the claim is that the whole polynomials, you can get them now by taking a limit where this s parameter tends to 0. So there's some sort of normalization which you need to take care of. I've just written it down here for completeness for anyone who ends up following. But really the important point is that I have that f lambda, which has been specialized now according to the star specialization. And there's also some reciprocation of the x variables that needs to happen. If I do all of this, then I will get the whole Littlewood polynomials. And you can sort of see how it's going to work just by looking at this formula here. Really, the only thing that we're trying to do is to turn that product there into the xi to the lambda I that we expect in whole Littlewood polynomials. So that's really the substantive part of the computation. Okay. So that's really the first goal of what we wanted to do in this lecture, which is really recovering the whole Littlewood polynomials via some sequences of specializations of the 6-vertex model wave functions. Okay. So this was principal specializations of the y parameters. And so now we're going to do something similar with the x parameters. Okay. So, okay, that's exactly what's written here. We're going to experiment now, perform a similar procedure with the x variables, which are the horizontal parameters that we have. And actually, computationally, what we're going to do here is actually do everything just in terms of the Cauchy identities and see what happens. Okay, so recall the whole Littlewood Cauchy identity. That's given here. So this is a formula that we saw previously. What we're going to do now is look at those x variables. So these ones here, and also showing up here on the right-hand side. And we're going to bundle those as well. So I'm going to take that collection of n variables and I'm going to split them up into bundles x with the superscript I. And the size of the bundles is going to be, again, denoted by j's. So obviously these are not the same j's as before, but I've just used the same letter. And so if we do this, you get this expression. So again, the first product here, this is a product over the, I guess, the bundle index. And this thing here is a product within each of the individual bundles. And so we end up getting this. And so then it's a very similar procedure as what we did in the case of the wave functions. it's actually a lot simpler because this expression is already simpler than what we had in the wave functions. And again, the idea is we would like to get some telescopic cancellations. And so what we'll do is, again, take the x variables and specialize them to some geometric progression in Q. And again, the base of this will denote it by S. So if we perform this procedure, we'll end up getting this expression here. Okay, so once again, when you do those splitting into the bundles and doing the geometric progressions, at the outset, the thing should depend on the bundle sizes, which are some integers, but you find that the final answer only depends on q to the ji. It doesn't depend on ji in any other way. And so then you can extend that j, which is taking some integer value, you can actually extend it into the complex plane. And at that point, q to the ji becomes like a complex parameter, which we can think of as its own indeterminate. And when we do that, we just relabel it, and we're going to represent it as this thing here. So minus ui divided by s. Okay, and all of this specialization, I'm using the same notation as before. So here, this is denoted by the red star. So the red star is again, this geometric progression followed by the analytic continuation here. All right, so the end result of doing all of that is this product here. And again, we notice that if we take that product and actually send the s parameter to 0 now, what will happen? Well, the denominator will go away and we'll just be left with this thing in the numerator. And that's precisely the right-hand side of the dual Cauchy identity that we also saw previously. So the result of doing that little computation is we actually get a theorem. So the theorem says now that, again, if we take some partition lambda and we denote its conjugate by the lambda prime, well, we actually have now that the q-Whittaker polynomials are given by, up to some normalization, which is not too important. They're given by taking a whole Lydwood polynomial, performing the specialization with the red star, and at the end of the day, very similar to what we saw previously, we have to send s to 0. And if we do this, we will get the q-Whittaker polynomials. So why is this a theorem? Well, let's go back to we started off with the whole Lydwood Cauchy identity. And what we did is we did that specialization of the right-hand side. And when we do that specialization of the right-hand side, it transforms it into the right-hand side of the dual Cauchy identity. And so it must be that performing that specialization on the left-hand side, well, it must actually transform, well, this whole thing here must transform into the thing which is paired up with a whole Lydwood in the dual Cauchy identity. And that object is precisely the q-Whittaker polynomial. So that's the reason why we have this result. So really, not by doing very much, just by taking those explicit formulas and just by plugging in these powers of Q, you get a lot of traction from that, and you're able to prove these very nice results, basically without very much effort whatsoever. So this is quite nice. All right. So yeah, so far everything I have said concerns the types of replacements that you have to perform in these formulas to make things work. But so far I didn't say anything about sort of the underlying combinatorics of the lattice models themselves. And so what we're going to look at now at the end of the lecture is the idea of fusion. And so fusion is really telling you what is happening at the level of the vertex models when I perform these geometric progressions in Q. Okay. All right, so yeah, I guess sort of due to time constraints and not wishing to make the lectures too technical, I'm really just going to give sort of a schematic presentation of what fusion is without really writing down any formulas. So I hope that maybe someone will put in the chat these sort of standard references for the stochastic fusion, for example, paper by Ivan and Leo. Okay.
Michael, there was a small administrative question, is whether you could change your highlight to green color to distinguish from existing highlights.
Okay, that's easy. So is this okay? Yeah. I hope. Yeah. All right. All right. So what do I want to say here? Okay. So yeah, we're gonna say something about the schematic idea of fusion, but I'm not going to really write down any formulas. So I hope that people who are interested, they can read up about these things. But basically, the idea is the following. So we have already seen that in order to go from 6-vertex model to the whole Littlewood polynomials, the thing that we did was actually to bundle up the vertical lines in this kind of way that we had here. And so what fusion does is it allows you to go from this kind of bundled picture that we have here, and it transforms that entire bundle into a single vertex, which is the vertex represented here. So really everything here is kind of schematic, but there are some important points to note. So the first point to note is that the fusion only works when you specialize those y variables to this geometric progression in Q. So you have to have this in order to have fusion working in the first instance. And well, when you execute the fusion, you end up getting a vertex as represented here. And the states that live on this vertex now are going to be a little bit different to the states that live on these vertices that live over here. Okay, so so as before, I guess the states that live on the horizontal line here, this is still going to be, in the 6-vertex case, this is still going to be 0s and 1s that live on these horizontal edges. But now I have this kind of fat line, which is really representing the fact that I have fused those vertical lines together. And the state that lives on the fat line now can actually be an integer now. So so it's going to be denoted by m, where m is going to be some non-negative integer. So actually the states that live now on that fat line, this has really been transformed into some infinite dimensional space now. Whereas in the what we started off with here, we actually just had all of the spaces being finite dimensional. And a similar sort of procedure works if we look at this thing here. You can take now a sort of square of these lines which are bunched up together, and in that case you can perform fusion in both directions, and you'll get to this vertex here, which is sort of 2 fat lines. And again, the dimension of both of the fat lines now is infinite dimensional. So again, we're going to have integers that live, non-negative integers that live on the 4 edges of a fat vertex. Okay, so I haven't really said anything qualitatively here about how the fusion works, but quantitatively, I should say, but qualitatively, this is what you get. Okay, so now let's have a look at the type of partition function that you get for the whole Littlewood polynomials, and you actually explicitly perform the fusion of that bundled wave function. Okay, so you end up getting the following. So as before, I have a partition lambda, and the whole Littlewood polynomials are then given by this partition function here. So the situation on the horizontal lines is unchanged. So the horizontal lines, they're still finite dimensional. On every single horizontal edge, you can either have a particle or not, basically. But now all of the vertical lines get replaced by these fat vertical lines. And the way we encode the partition of the whole derivative polynomial is it's encoded via its part multiplicities. So those part multiplicities will be some non-negative integers, and we put those non-negative integers at the top of all of the fat lines. And so we have the situation now where you have your n particles coming in, and they're going to traverse through this lattice now in some way, and then find themselves going out at the top. So it's very similar to the 6 vertex wave functions, but the difference is each of the fat lines now, you can actually have lots of particles passing through a fat edge. And so explicitly, the vertex weights that you get here are given by the expression we have here. So I have 4 different types of vertices. And so here I'm using this m to denote the number of particles that enter from below. And as before, m is taking values in the non-negative integers. And you see there are 4 possibilities. So here I have m particles coming in, and then m particles leaving via the top, and nothing happens on the horizontal edges. In this case, I have m particles coming in from below, and one of them decides to turn the corner and go to the right. So then I have m minus 1 at the top. And this is really the sort of the opposite situation where I have m coming in, and here one of them joins the bundle, and then I have m plus 1 leaving at the top. And the final case is where I sort of have a particle which is, well, this one is joining the bundle, but at the same time, there's another one which leaves the bundle. And in that case, you have the conservation of this number. All right. So in terms of the weights of those vertices, well, they actually end up being very simple. So as you might expect, whole Edward functions, these are polynomials. So it's no surprise that the weights themselves are no longer going to be rational functions. They actually depend on x in the polynomial fashion. So actually only 2 of them depend on x, which are these 2. And the other weights here, these are just equal to 1. And this one has some non-trivial dependence on q. But this is really the only way in which q enters the partition function. And so that's the claim. This is the lattice model formulation of the whole Edward polynomials that you get by doing the fusion that we have described. And so in particular, I hope that answers Rick's question from earlier about a non-intersecting lattice path formulation of the whole Edward polynomials. Well, they're not non-intersecting lattice paths, but this is really the closest thing that we have available for that. Okay. So I'd like to mention some variations on this formula, which will be useful in what follows. So we're going to look at 2 variations. All right, so here is the first one. So what I'm going to do now is I'll take my partition, and I'm just going to focus on the parts of the partition which are actually positive. So I'm just going to throw away all of the zeros. So I'm going to have a partition with L positive parts now, and then I'm going to fix capital N as before to be something bigger than L. All right, so the claim is the whole Edward polynomials, we can actually represent them in this way here, which is a little bit different from the formula that we had above. So what's the difference? Well, previously we had particles that entered along here, right? But this is no longer going to be the case. What's going to happen now is all of the particles will actually enter via the base of that 0th column, if you like. So I'm going to have L particles that come in from here, and then they're going to propagate, in whatever way they want through the lattice. But all of the incoming particles come through the base of that first fat line. And then they leave at the top in the usual way. So I have these part multiplicities up here. Okay. So the claim is that this thing here up to this normalization, this is also giving me the whole Littlewood polynomials. All right, so this is a nice little exercise if you want to get used to the sort of combinatorics of this model. It's pretty easy to prove that this thing here actually coincides with the first representation of the whole Littlewood polynomials. Essentially, all you have to do is compare the two formulas and really focus on just that first column. So, so this column here. You just have to focus on what can happen in there and compare it with what can happen combinatorially in this one here. So if you decompose over that column in both of those formulas, you'll be easily able to match the two things up. Okay, so that's the first variation. And the second variation is actually quite nice. Yeah, so at this point, the lecture gets a little more complicated, unfortunately, but that's the nature of working with these higher rank vertex models. So actually, the model that I gave above, so this model here, this is normally referred to as Cubozone Model. And we got it by taking the 6-vertex model and doing some sort of fusion procedure on it. If we start off from the colored 6-vertex model that I introduced in the previous lecture and perform the same fusion, well, then you will get a colored Cubozone model. And the colored Cubozone model looks like this. Okay, so there are a few more vertices to take care of now. So what do I have here? So, oops. Okay, so if I look at each one of these vertices, at the base now, this is no longer going to be just an integer, but it's going to be a vector with non-negative integer entries. So it's going to be a vector of little n non-negative integers. And what those non-negative integers are representing is the number of particles you have of each of the n colors that you have in the model. All right. And so now we can see that the principle of the model is similar. So what can happen? So here, for example, you see that the vector is just preserved, so nothing changes. But in this one, I have here the A that comes in from below. And now one of the particles of color I decides to turn the corner. And so in the corresponding vector at the top, the ith entry of that vector is then reduced by 1, which is the meaning of this notation. And in a similar vein here, I have the vector which enters from below, and I have a single particle of color I, which then decides to join the bundle, and that then means that this vector, I look at the ith component, I have to shift it up by 1. And so that's the meaning of the notation, and I hope the remaining ones then conceptually clear what's going on. All right. And so each one of these has a weight, which is indicated by the green underneath here. But again, the important thing to note here, these are just polynomial weights in X with some additional Q dependence, which is given along here. And actually the final vertex is just equal to 0, so it has weight 0. So it's actually forbidden. Okay. So this is our model. And again, as I said before, this is the model that you get by doing the fusion of that colored stochastic 6-vertex model. Okay, so now here is the the second variation of the whole-Littlewood polynomials. So the claim is that I can represent whole-Littlewood polynomials by this partition function now. So what I have now is at the base and at the top of every single column, I have a vector now, which is representing, the colored particles that are entering the vertex and leaving the vertex. So these things here are vectors in exactly the same way as up here I have vectors. All right, so the claim is I am going to take, at the base of this column here, I'll take a vector A. And at the top of the first column, I'll take vector B1, here vector B2, etc., etc. And these vectors, they have to satisfy some constraint. All right, so the first thing is, as I said previously, they're vectors with n components, each of them being non-negative integer. And so the first constraint is that if I look at the A, this has to be equal to the sum of all of the B vectors. So what this is saying is that the particles that enter from below have to leave via the top somewhere. So this is actually, this is really just conservation of particles. So that's the first constraint, conservation of particles. And the second constraint is that if I sum up all of the components of the vector A, then that sum has to be equal to L. So the L, just to remind you, that was the L that we had here. Okay. And in a similar vein, you can see that here I'm supposed to have these part multiplicities at the top. And so that means that the sum of the B vectors has to be equal to these part multiplicities here. And so the claim is if I take any A and any set of vectors B that satisfy these constraints, this will give me the whole-Littlewood polynomials. So actually, this is not really just one formula for the whole-Littlewood polynomials. This is really, a whole lot of different colored formulas for the whole-Littlewood polynomials, and all of them work. No matter how you choose to do the coloring, as long as it satisfies these constraints here. And the reason why it works, of course, is behind all of this, there is a kind of color blindness property, which I'm not describing here, but we saw in the first lecture that there is this idea of color blindness that happens in these colored vertex models. And here there is a color blindness property that makes this thing be equivalent with just the rank 1 version that we have above. Okay. Covers the previous expression when n is equal to 1, because when n is equal to 1, the vectors just become vectors with one component, and then we get back down to the rank 1 situation. But there's another interesting case, which is where we take the A vector here to actually just be collection of ones. So all of the components of that A vector, they're all just equal to ones. So I have 1 to the n. And this, to take a phrase from the long paper that we have with Alexei, we refer to this as the rainbow case, because you have exactly one of each of the colors in the partition function you're looking at. And so I've done a little example here, which hopefully will make it clear how things work. So the example here is lambda is equal to 4, 4, 2. So this is our partition. And we're going to look at the whole-Littlewood polynomial in 4 variables. So I have 4 variables, so I'm going to have 4 rows. And what I'm going to do is take now 3 particles to be incoming at the base of this column here. So this is a particle of color 1, particle of color 2, and one of color 3. And if I represent that in terms of the vector, that would just be the vector 1, 1, 1. Okay. And so what happens now is those particles going to propagate through the lattice, and one of them has to leave at the top of this column. So this is the column that corresponds with this 2 here, part of this partition. And the other 2 particles have to leave via the top of this column. And we have 2 going out there because we have 2 4s. Right? And in terms of the vectors, this would just be the vector 1, 0, 0, and this one is going to be 0, 1, 1. Okay. So the claim is you work out the partition function of that thing. So you have to work out all possible ways for the particles to go from their starting place to the finishing place. You work out all configurations. You work out the weight of every single configuration using this table of weights that we have here. And at the end of the day, you get the whole little polynomial. So this is the claim. And notice that, and this is kind of a remarkable fact, the result does not depend on how I order the colors at the top. So actually, I could decide to have put here, instead of a 1, I could put the 2 instead. And likewise, I could have, instead of the 2, I could have actually put a 3 here. Right? As long as you have particles going out at the correct positions, doesn't matter how you color them, you're still going to get the same result. And this is the idea of color blindness. Okay. Okay, so I'm getting now to the end of what I want to say. I think I should be able to finish. I guess we have normally about like an hour and 15 minutes. Is that the normal running time?
Yeah, that's right. But if you need a little more, it's fine.
Okay. The other option is that we break here, and then I come back with the Whittaker at the start of tomorrow's lecture. I don't know what's preferable.
Whatever you're more comfortable with. It's midnight for you. It's after midnight for you, so that you may also want to consider.
Well, okay, I have. Yeah, there's still a bit here, so I think probably we should maybe break there, and then I'll
okay. Yeah. That way people won't get confused at the end.
That's it. That's what I think. Sorry. Yeah.
Okay. So let's thank Michael. And we do have time for questions. There's been a very active discussion in the chat, but people can bring more questions to Michael's attention. So there was one question from earlier that I'm not sure got totally resolved, which is whether there's a version of so you give a Cauchy identity between, I guess, the Hall-Littlewood and the q-Whittaker.
Yes.
And so one knows that q-Whittaker goes to Whittaker. So there was a question as to whether there's any sort of limit of that, and the t goes to 1 limit related to the Hall-Littlewood as well, and where you have a sort of dual q-Whittaker, or a dual Whittaker or something, Cauchy identity. I think that was the question.
Right. So I mean, as far as I know, like the t to 1 limit of Hall-Littlewood's is not very interesting. I mean, just the naive t to 1 limit is just giving monomial symmetric functions. So you would have to perform, I guess, some sort of non-trivial scaling there to get something.
Which anyway you need to do to get to the Whittaker.
Yeah. Yeah, offhand, I don't know if that has been looked at. Yeah.
I've looked at it at some point in the past, if I can interject, and the issue is the right-hand side is a little bit too degenerate for such limits. There's no Q anymore.
I see. Well, yeah.
Okay, so Hugh has a question about this bundling and putting particles as far to the right in the bundle. When you have colors, what do you do? Are they sorted? Do we sum over all possible orderings?
Yeah, that's right. So yeah, I didn't say too much about this, but sort of the way that you organize the is not terribly important. And so the reason for that, well, I didn't really explain too much about how the fusion works, but there is a certain property, which is the Q Exchangeability Property, which, yeah, maybe let's go back to the picture. Yeah, so in this picture here, you know, you might ask, you know, what would happen if, you know, if I take, say, this particle here and shift it to the left by 1 step instead of having them all flush to the right. And the answer is, if you move that thing across by 1 step to the left, you get the same object up to a power of q. You get extra power of q. And so actually, you know, in this formula here, I didn't say too much about the normalization, but this factor here, there's actually triangular numbers of these q's that are showing up here, and that's precisely coming from these overall powers of q that you get in bundles where you have more than one particle. You get some sort of triangular numbers for the exponents of the q. So I guess to answer the question, it doesn't really matter too much about how you arrange things at the top. All that will happen is you get overall powers of q, and that will also be true in the colored case.
There's another question. I don't know if you can about color blindness.
Color blindness, can you explain it a little bit more? Yeah. Should one work in all possible permutations of colored particles? And what quantity stays invariant under these permutations? Okay, yeah. So indeed, I kind of glossed over this. So yeah, let's go back down to the picture. Yeah, I didn't want to put this in the slides as well because it would get too confusing. But so we have seen in the previous lecture that the way that we described color blindness is you actually have to sum over the permutations of the colors at the top. So that's how I described color blindness in the first lecture. You fix the positions where the particles go out, but then you sum over all permutations of the colors at the top. And the claim is if you sum over all permutations of colors at the top, then you will get just the black and white object. You get the colorblind object. So here I'm not doing that. So why is it the case that this thing is colorblind? Well, the answer to that question is there is another version of the colorblindness where instead of summing over the particles at the top, you sum over the incoming particles. So you actually symmetrize over the colors that enter the lattice. And that also gives you a color-blind object. So actually here, you see that all of the particles here are actually entering via the same column. They all come in via the 0th column. And so here there is no symmetrization to perform. There is no permuting of colors to perform because they're all entering in the same column, so I cannot permute this in any way. So this thing is already summed, if you like, or set up to be a sum over all permutations in such a way that we can already invoke color blindness. So this is really a colorblind object because of the boundary conditions, because all of the particles are entering via that column there. So that's the reason why this thing ends up being colorblind. So there is a sum over permutations happening here, but it's a trivial sum. Okay, question from Matteo. Whole-Littlewood functions have a combinatorial version called modified whole-Littlewood polynomials. Is there a similar object for colored functions. Yeah, so so actually the modified Hall-Littlewood polynomials and the q-Whittaker polynomials are really one and the same thing. So it's really something that I personally don't see any distinction between them. And in tomorrow's lecture, we're going to give a colored version of the q-Whittaker polynomials. And that colored version of q-Whittaker also works for the modified Hall-Littlewood. So yes, the answer to the question is yes. Okay.
Any other questions for Michael?
Can I ask one final question?
Yeah, Dan.
Yep.
I'll ask my favorite question as usual. Do you see the determinantal or Pfaffian structure when, I don't know, q is equal to -1 or 0? Of course, q is -1 is more interesting, but 0 would be fine as well.
Right. I mean, so when q is equal to 0, you get to this phase model that Bogolyubov talks about.
Yes, but it's sort of hard to see that structure there. I was wondering.
Yeah, from this you do not see straight away the determinantal structure, but I mean, if you take the sort of combinatorial object that you get there, and you have these compressed paths now that you have many paths that can occupy a fat edge. If you decompress this object, you just get back down to non-intersecting lattice paths, and then the determinantal structure is obvious. So certainly in the q equals 0 case, there's a kind of decompressing procedure that will allow you to see the nilps. In the q equals -1 case, I would say something similar should work, because when q is equal to -1, you essentially forbid ever having two paths coming into the same vertex. So if we go back to the vertex weights, yeah, back here. So this vertex here has a q to the 1 minus q to the m, and when m is going to be 2 or greater, well, when m is going to be equal to 2, this thing is going to vanish when q is equal to -1. And once you forbid the possibility of having two particles coming in, then you can never have 3 or more. So one gets back down to a kind of 6 vertex type object, which I think one should be able to see the Pfaffian structure directly. So I think the answer is yes in both cases. Okay. Question from Matteo: do colored functions have a colored Schur expansion? I'm not sure what you mean by colored Schur. Can you clarify? Do you mean like something like non-symmetric Schur? Is this what this means?
Yes, my question is the colored Schur like what you would obtain by sending q to 0, like some sort of Demazur atom or some different object?
Yeah, that's right. So I think depending on the object that you do the limit of, you either get the Demazur atoms or Demazur characters. And yes, I mean, there are some colored functions that I know of that allow you to work out the corresponding expansion in terms of Demazur atoms or Demazur characters. But yeah, in general, these Schur type expansions, this is a very difficult business. I don't really advise anyone to get involved in this. I personally spent quite a bit of time looking at these kind of Schur expansions, and that tends to be a much harder problem than just trying to write down lattice model expressions for the polynomials. The Schur expansions are like an order of magnitude or 2 orders of magnitude more complicated than just writing down the polynomials. So, yeah.
Okay, well, maybe we should let Michael get to sleep. Let's all thank Michael again for his second lecture. And it'll be the same time, same place tomorrow, so 9 a.m. Eastern time, whatever time it is your time. So we'll break now for, I think it's 40 minutes, and I'm going to close out this Zoom, and then I'll immediately reopen it for anyone who wants to join, just so we don't have phantom Zooms. And the next lecture will be Fabio Toninelli's third lecture, followed then by Hugo and Rick, their lectures. So we'll see you in a little.